Hello folks, and how are you all doing? So in this video, we will be coding this very simple neural network without using any libraries in JavaScript. So why JavaScript? Why not Python? Because we are not using any libraries, it really doesn't matter. We will try to understand how neural networks work in general, and we can use any language for that purpose. So here what do we have? So we have a very simple model here. It's nothing fancy. So we have some blue balls, some grayish balls, and some red balls. So the balls you can also call these neurons, very similar to our brain. It is like a mini brain that does some arithmetic operations. So here we have two inputs, 2 and 3. And as we can see, every input is connected to one of the grayish balls, actually all of them. So two lines with the first ball, then the second ball, then the third ball. And all of the gray balls are connected to the red balls, which is our output layer. So what we are doing today is basically we are taking some inputs and we are expecting the outputs to be the sum and their difference. So we have 2 and 3, and when we add 2 and 3 we get 5, and when we subtract we get -1, and that is what our outputs will be. Now this is very simple arithmetic. There is no need to use neural networks for this purpose, but why we are coding this is because we want to understand how neural networks work. Neural networks don't understand arithmetic. They have a different way of calculating the outputs, but we will see that the outputs will be very close to what we are getting here. So you can consider this like a child. When a child is learning something, he may not exactly understand why what he is learning or she is learning. So for example, a child may try to recognize tigers and lions by looking at some images. They may not understand like why this is a tiger, why this is a lion. Maybe we also don't understand even now, but the child will understand some patterns, and this is how we think in general. And they will develop some intuition, and then after a while, after seeing a lot of images, they will be able to distinguish between what is a tiger and what is a lion. So similarly, something very similar this model will also do. And here, as you can see, above every line there are some small numbers. So these are like weights, and all the hidden layers and all the output layers, they also have some numbers attached. These are what we call biases. Now these gray balls are called the hidden layer. Now there can be one or many hidden layers. This is a simple model. We have only taken one hidden layer. So hidden layer is like a lot of neurons that actually help us in our decision making. So let's say if this neuron, this the above one, this one is very powerful, it may actually bias our decision towards the red ball over here. Another neuron may take us to another output. So if you think that when we are trying to take a decision with our brain, we have some biases, some preconceived ideas, and also when we are thinking, it is basically we are using these weights, these small numbers, to adjust our decision. So exactly that is how this kind of models work, and that is how scientists thought of models like this, something very similar to our brain, but using mathematics and using computational models to predict. And it works very well, and we will see that exactly today. Now let's go back to our VS Code and let's try to code this thing. And yeah, we'll see how neural networks work. And I am at my VS Code, and I will start by creating one ann.js file. ANN stands for Artificial Neural Network. And I will start by defining the structure of our network, which is our inputs, hidden layer, and outputs, whatever we have. So I will write input count equals to 2. This is the number for input neurons, input count. And then we will have the hidden count. So we have 3 hidden layer neurons. And lastly, we have the output count, and we have 2. Now, after this, we have to define our weights. Now, the weights are the numbers that we have in the lines connecting to neurons. And we will be starting with these weights. Generally, we can initialize weights. It can be anything between -1 and +1. But for this network, we can start with whatever weights we have here. And anyway, these weights will be adjusted, and accordingly, our network will work. So we have our hidden weights. this will be a two-dimensional array because we have two inputs and three outputs. And yeah, so that makes it 3 cross 2. So every neuron, input neuron, will be having three associated weights with three hidden layer neurons. And combining the input layer and hidden layer, you can also call this as level 1. And then the hidden layer and the output layer, it will be the level 2. This is also another way to describe the network. So yeah, so let's write our weights. So we have 0.2, then minus 0.1, and then minus 0.3. This is the weights associated with our first neuron. And then we have 0.3, then 0.2, and then 0.5. And after the weights, for the hidden layer neurons, it will also have a bias. So hidden bias, and our hidden bias is minus 0.5, 0.1, and 0.2. So whatever is written over here. Now after this, with the weights and biases, we will be having some hidden layer values. And then using those values, we will calculate the output layer values. And we will compare the output layer values with the 5 and minus 1. And accordingly, we will get an error. And that error will be used to adjust the network. So we will do that. So after the hidden weights and hidden bias, we will need one more thing. And that is called hidden values that we will calculate. For now, this will be an empty array. Now, after the hidden weights, there will be our output weights and the output bias. Now, for the output weights, the structure will be 2 cross 3 because this time there are three hidden layer neurons which is connecting to two output neurons. So every hidden layer neuron will have two associated weights. So it will have 6 weights in total, but the structure is 2 cross 3 and not 3 cross 2 like the hidden weights. So here for the first neuron, our weights were 0.4 and minus 0.2. For the second one, we have minus 0.2 and minus 0.3. And for the third one, what we have 0.1, 0.5 and 0.1. Yeah. And then we will also have the output bias. And we will have two this time because there are two output neurons. And we had minus 0.15 and minus 0.4. And also after the hidden values, we will also have the output value. Value or values, whatever. Yeah. So now we can start writing the code that will run in our network. And the first thing that we will write is called a feed forward algorithm. Feed forward. So feed forward is basically using 2, 3, we will calculate some values in the hidden layer. And using those respective values, we will calculate the values of the output layer. We will get the errors. And then using those errors, we will adjust our weights and biases, which is called backpropagation. So all of this together is one iteration of the neural network. And we will do many such iterations over many, many inputs and outputs. And that is how our model will be trained. So for doing the training, we will need lots of data. And this data is not something that we will write like 2, 3, 5, 1, whatever, whatever. This is something we will create. So let's see how we can do that. So feed forward, after that we will have a back propagation. And here for generating our training data, we will create another file called data.js. So what we have in this file, we will have something called data. This is something that we need to export. Now this data is actually an array, and that array will contain an object, and every object will contain an input and an output. So let me put it this way. Let's remove the data for now. For now, let's write input 1. This is our first input, and this will be a random number. And for ease of calculation, I want the numbers to be whole numbers. So math.floor and then math.random. Let me take a number in between 0 and 25. And we want negative numbers also, so we will do a minus 12. So we will get a number in between minus 12 and plus 12 like this. And we want two inputs, so input 1 and input 2. Now, if we have these things, what do we want to export? So let's say we have a function that will generate one set of input and output. So let's name this function as generate data. And this generate data will first of all have the input and an output. And then we want to return an object. This object will contain input, and the input will contain our input 1 and input 2, like this. And then we will have the output. So the output will contain input 1 plus input 2. This is our first output. And the input 1 and input 2 minus input 2. This is our second output. Now, this thing will work definitely, because let's say input 1 is our 2, input 2 is 3, then we will have whatever, 5 and minus 1. To verify, let me simply write input 1 as 2, and let input 2 as 3, and let's see what do we have. So log of generate data, and let's see. So we will do node of data.js, and what do we have? The output is 5 and minus 1, which is basically our network, this one. So when we are training, we will generate lots of data like this, but for now I think one data is fine. But yeah, uh, now we need to export, because this is a different file. We can of course use this one directly in the init, but let's keep the file separate. So what we will do instead is, now we will write the data that we were initially writing, and this will be an array from, and here we can generate lots of things. For now we will generate only array of length 1, and we need to call this function here. And then lastly, what we will do is export default data, and then we will be able to import the data over here. So import data from where data.js. Now after this one, we can do an output of the data and see what do we get. Output. Ah, there is no need for backticks or anything like that. Okay. So we need to run the ann.js, not the data.js, not this one. So they're saying that okay, they're not able to find or something like that. It should be like this. Yeah. So as we can see, we have the input as this one and the output as the 5 minus 1. So we have this one. Yeah. So now let's see how we can write the feed forward. So to write the feed forward algorithm, we have to first of all loop, because we have 2 inputs and 3 outputs, and we have to go through each one of them. And so we need 2 loops, one iterating over the hidden values, and the other one that will iterate over our inputs. So for let I equals to 0, I is less than our hidden count, and then I plus plus, and then we will have another one that is for let j equals to 0, then j is less than our input count, then j plus plus, and here we will also define a sum. So let sum equals to 0, and here we will calculate the value of the sum. So sum plus equals to inputs j. Now this inputs is not defined. So what will this input be? So this inputs is nothing but, so let me define it like this. Let inputs equals to data dot input. Let me put it like this: data 0 dot input, and let we can name it outputs or something like that. Maybe output value. Yeah, we have an output value. What we need to define is this one. The output value is basically the value we will calculate. But this 5 and minus 1, let me name it as given output value, because we will need this data for training. So given output value is our data 0 dot output. Yeah. And if you do a console log of not this one, let's do a console log of the inputs, and then the given output value. Let's see what do we have. We have whatever we need, we have that one. So yeah. So what will be the sum? So first of all, this I is looping through our hidden count. So basically it will loop through 3 times, and the j is looping through our input count, so it will loop through twice. So what do we want with these loops? So first of all, we have this 2. So let's say we want the value of this particular neuron. So here, what is the data? So we have 2. with a weight of 0.2, and we have 3 with a weight of 0.3. So the result of this neuron, the value of this neuron will be something like this. Let me make it smaller. So 2 multiplied by 0.2 plus 3 multiplied by 0.3, and then we have a bias of 0.5 minus 0.5, and so what is the result? It is 0.8, I believe. Yeah. So 0.8 will be the value of this neuron, and this is what we are doing in this for loop. If you can see, so we will loop through 3 times, and here we are looping through twice. So we are taking the first input, and we are adding what? We are adding, not adding, we will multiply the respective weight. So this is our hidden weights of ji. So this will loop through twice, and we will get the respective results. And lastly, we also have to add the bias. So hidden bias of I. And lastly, um, we have some hidden values that doesn't have a value right now, but here we will store that one. So hidden values of I, and here we will assign the value of sum. Now, if we do a console log of the hidden values, we will get whatever we have. So the first one is 0.8. And yeah, so for sometimes for calculation, this kind of issues come, but yeah, as you can see, it's 0.8. Then the second one will be 0.5, and the last one will be 1.1. So the second one, let's see, 2 into minus 0.1, this is minus 0.2, and this one is zero point 0.6. Zero point 0.6 minus zero point 0.2 is 0.4 plus zero point 0.1 is 0.5. So second one is also correct, and so and so. I mean, yeah, it will be correct only because it's such a simple addition and subtraction. Yeah. So, but one thing we should keep in mind is that so these calculations and this feed forward and training, whatever we are doing, this will work for this case because we have 3 inputs and we have outputs as 5 minus 1, and both are linear operations. So one is addition, one is subtraction. So very simple operations. And generally, these hidden layers also have some activation functions. We are not using any in this case because it's such a simple operation. And because we are not using any activation functions, we may consider that we are using a linear activation function. So what activation functions do is whenever we have a value of, let's say, zero point 0.8, we will generally not use this zero point 0.8 value. The activation function will change the value. Accordingly, we will proceed. And so a similar process we will follow for adjusting the errors also. But here that is not required is because, as I have told, this is very simple operation. But for complex operations, we may need to do more. But yeah, let's not worry about that right now because right now we are keeping things simple. So last one is our 1.1. Yeah. So these are our values for now. Okay. So our feed forward for the hidden layer is done, and then we will move forward to our output layer. So this is for the hidden layer. For the output layer, it will be very similar. So for again, we will have 2 for loops. So let I equals to 0. This time I will be less than the output count. This is 2, I plus plus. And then again, we will define the sum to be 0. Again, another for loop. So for let j equals to 0, j is less than, this will be the hidden count because we are taking the hidden count as inputs, and then j plus plus. And then we will similarly calculate the sum. So sum will be hidden values, the hidden values that we got just now, j multiplied by our output weights of ji. Yeah. Then we will also calculate the bias. So sum plus equals to our output bias of I. Yeah. And lastly, we will store this in the output value, which is an empty array that is defined above. Where? Let's see. Here. So output value of I will be whatever is our sum. And then we will do a console log of the output value. We are writing value, but it's actually values. And yeah, we have 0.62 and minus 0.6. So let's see, we get the same values or not by doing a manual calculation. So here we have 3 neurons in the hidden layer, which is taken as the input layer for this layer, for this level, you can say. So we have 0.8 into 0.4. So this will be 0.32, right? And then we have 0.5 into minus 0.2. So this will be minus 0.1. And then for the third one, we have 1.1 into 0.5. So this will be plus 0.55. And lastly, we have the bias of minus 0.15. So minus 0.15. And if we add and subtract, what do we get? So we have to 0.32, 0.22 plus 0.55 minus 1 by 0.4. So 0.22 plus 0.4 is 0.62. And we have the same value over here. So yeah, this is correct, definitely. And accordingly, we are getting, so this is perfectly fine. So we have 0.62 and we have a minus 0.6. Let me make it smaller. We don't have enough space. 0.62 and we have a minus 0.6. Yeah. So now the thing is the given output value is 5 and the value we are getting is 0.62. And here the given value is minus 1 and the value we are getting is minus 0.6. So there is a huge difference. Here the difference is 4.38 and here it is, I believe, minus 0.4. Huge difference. So now, depending on whatever errors we have, so this can be called as errors, we have to adjust the width, like the whatever width and biases we have. And then the next time the calculation will be a little bit better and better and better. In this way, if we train for 1,000 iterations, we will have something very close to the results. Yeah, so that is what we will be doing now. So yeah, so now we have to start our back propagation. And for that purpose, first of all, we have to calculate the errors. So output errors. So first of all, we have to create an empty array of output errors that is not yet defined. And then we need a for loop. So let I equals to 0 and I will be less than the output count because we are starting from there, I plus plus. And here we have to basically subtract the values and we will assign the same to the output errors I. So whatever output value we got, output value of I minus the given output value of I. Given output value is basically 5 minus 1. Yeah. And we can log this one also. We already know what will be the log, 4.38 and whatever. But let's see how we can adjust the weights. That is the more important part. So output weights and bias adjustment, you can say. Adjustment. Something weird I have written. And here we again need a for loop because we have to adjust 6 weights. So the first one, we will loop through the output count, I plus plus. Then we will loop through the hidden count. J is less than hidden count, J plus plus. And here we need to define something called a gradient. So what is a gradient? A gradient is like in coordinate geometry, you may have heard that this is what is called a slope. You can consider this to be a correction value. So what is a gradient? So we will have an output error for I related to the output. And for each of the hidden values, we will have a gradient. So we will multiply that with the hidden values. So one for each output, for each hidden value. So 2 cross 3, 6. We will have 6 gradients. And then we will have some new output weights. So output weights. So output weights of Ji, because there are 6. And this will be, we will subtract the value of the output weights by little bit. And here we will, the gradient will come into the picture. So we will subtract by gradient, but actually not entirely by the gradient. We don't want to do that. We want to make the value of the gradient much smaller so that in one iteration only we have a little bit of correction. Then the next iteration maybe a little bit more. Because if we correct by a large value, so for example, here the gradient may be large. For example, here we have a 4.38, right? Here the output value is what? 4.38. And let's say we want to correct this minus 0.2, this one. So we will do a 0.5 into 4.38, and as you can see, the value is 2.19. It is a huge value, but we don't want to subtract like that. We want to make it smaller, and in that way, the training will be much, much better. So we will have something called a learning rate. So for each iteration, how much you want to learn or adjust or whatever you can say. So it's like when a child is learning by looking at pictures, the child may not learn something on the first try. Let's say the child is learning what is a dog and what is a tiger, two very different animals. But yeah, anyway, well, let's say dog and a cat, very similar. So the child may have to see lots of dog pictures, and only then the child can understand what is a dog by looking, I mean, professionally, like how we understand. So yeah, the learning rate, if it is smaller, it is actually better. Yeah, it is not like, in school, if you memorize faster, you are smarter. It's not like that. I mean, in many schools. So learning rate is something that we will define and it should be very small. So we will define it as 0.002. Yeah. And here, so this value will be much, much smaller because we are multiplying by a small value. And yeah, this is how we want to adjust. And similarly, we want to change the output weights also. I mean, we have changed the weight, so we want to change the bias now. So output bias of I, we also want to change it by learning rate into our output errors I. So output errors of I. Yeah. So this is our adjusted weights and bias. So we can once again do a log of output weights and then a log of output bias. And let's see what values we get. Bias. Uh, okay. So node. Yeah. So we got the errors here, and these are the adjusted weights and the adjusted bias. So if we compare this with our original weights, so for example, this is our output weights, and this is our adjusted weights. And if you can see, it is changing a little bit, right? Because the learning rate is small, it is changing a little bit. Let's do one thing. Let me increase the learning rate to zero point 0.2, and you will see there will be a huge change. As you can see, this is the new one. It is 1.1 something, and here it was 0 0.4. Yeah, you see the difference. So this is not something that we want. We want to make it smaller. And yeah, so these are the changes, and these are the changes in bias. We will generate lots of data from the data.js file. Instead of one, we may generate 100. And for each data, we may train multiple times also. And in this way, we can train our model. Okay. So after adjusting the output weights, now we have to adjust the hidden weights and hidden bias. And then we are done, basically. So to adjust that one, we have to get the hidden errors also. So let me define hidden errors. This will be an empty array for now also. Now for let I equals to 0, I is less than my hidden count, I plus plus. And then for let j equals to 0, and then j should be less than my output count. Um, yeah, this is output count, j plus plus. And then what do we want? The hidden errors plus equals to my output errors plus output weights. And this time the output weights are the adjusted weights. So output weights of ij. Now I think this may throw some error. So errors first of all, and errors, because this hidden errors does not have any value. It should be hidden errors of I actually. And this hidden errors does not have any value. So what we need to do is first of all do a hidden errors of I equals to 0. And in this way we can get the hidden errors, and then we will log the hidden errors, and let's see. So when we are calculating the hidden errors, we are using a different approach. We are not like directly subtracting it from the hidden values. Why we are not doing that? That is because our output weights have changed. So here the errors calculation was done by simply subtracting this with this. But here we have these values, but we don't know what the original values are. There are no original values. So what we are doing is we have the weights associated with the hidden layer and the output layer. and those weights are adjusted, and we have some errors from the output layer. So we are doing some sort of a back calculation, and so this entire process is called back propagation. So it is not that straightforward, but it's not much complex also, as you can see. So what we are doing is we are going through the hidden count and the output count. We are looping through this one. Every hidden error is taken as 0, and we are increasing the hidden errors depending on the output errors associated and the output weights. So this should be output errors of j. Yeah. So for one output, like this will be, we are looping through twice, and we have one output error and the other one next time, and we are multiplying the associated weights. So that's all we are doing in the backside. So yeah, hopefully this is not too complex, but yeah, this is how we will get the hidden errors, and let's see what we get. So yeah, so this is our values of the hidden errors. We cannot compare it with anything because we don't have any real values. So this is something that we need to deal with it for now. But now is the interesting part. So we have to adjust the hidden weights and bias. And this is again very straightforward and very similar to the output weights and bias. So it will be very similar to what we have written over here only. So here I equals to 0. I should be less than the hidden count I plus plus. Then again another for loop for let j equals to 0. And then j should be less than the input count, that is the first layer, and then j plus plus. And lastly, we will again have another gradient. So this gradient will be hidden errors of I multiplied by my inputs of j. So inputs of j. And then accordingly, we will adjust the hidden weights. So hidden weights of ji should be little bit less. So this is what? Gradient into learning rate. And lastly, we will also adjust the hidden bias. So hidden bias of I is less than, not less than, we are subtracting learning rate into hidden errors of I. That's all. And then we will write our hidden weights and log of our hidden bias. And let's see, what do we have? So we have a new set of hidden weights and hidden bias. So if we compare it with the original, so the original is this one 0.2, and here as you can see it is little bit more. Then minus 0.1, it is little bit less. The bias is also little bit less, little bit more, little bit more. Now this is also a little bit more actually because it's a negative. So this is how we are adjusting. So now this completes one iteration. So we have inputs, we have outputs, and accordingly we have adjusted the weights, and one iteration is complete, but one is not enough. We need many, many, many. So for many iterations, what we need to do is first of all, instead of one, we should export a lot of data. So this is length of 1. So let me do it a length of 100. And in the ann, what we will do is here, let me log the data also. And let's see what do we get. So as you can see, we have a lot of, okay, so everything is 2, 3, and 5 minus 1. And that is because we have to remove these two lines and we have to take these two lines. Yeah. So now this will be much better. So now if we go above, as you can see, we have a variety of inputs and a variety of outputs. And this is what we will do to train our model. Yeah. So, so to do this, what we need to do is we need to create a loop, of course. So here, what we will do is for, we cannot use I or j. We can use actually, but let's use another variable because I and j is being used already. So let k equals to 0, and then k should be less than data dot length, and then k plus plus, and this will end at the end. And here we need to define our inputs and our outputs. So here we are taking inputs. So the inputs, where are the inputs? So inputs is here. So what we will do is Let me take these two lines first of all and comment out this also. And here, um, let me do it like this. We have inputs and given output value. Instead of 0, this will be k, and this will be k. And here we will declare let inputs and let given output value. And we can simply remove these lines also. It's not required. Let me comment out the data also. Yeah, let's also comment out these lines. I think this is not required. And now, as we can see, we have a lot of things actually. Um, so it's not clear which is what, because this loop is running through 100 times because length of data is 100 and we have a lot of data. So let's try to give it some more sense of what is happening over here. So what we will do is at the end, we will write a log, and this log will be iteration and the value of k, then input, and this will be our inputs basically, inputs, and lastly the output will be the output. uh, this should be, let's say, so output, and yeah, so let's see what do we get now. Okay, output is not defined, so because this should be output, not output. Okay, so this is not output, so what is this? Okay, this is given output value. But here I'm not sure we should be doing what, given output value. Okay. So input is this one and output is this one. But what we need is actually the outputs that is calculated by the network. So that network output is actually this output value, right? So what we will do is given output is this, and then network output is what is our output value. Yeah, now let's see what do we get. So as we can see, input is -1 and 9, given output is 8 and -10, and our output is something else. It doesn't look like the network is trained enough. And here we can see given output is 0, 12, and here the output is 2 and something else. Okay. We can see the weights are getting adjusted, but it's not close to the training. So what we want to do is we want to add some more things also. So we want to add something called epoch. So inputs given output value. So these epochs will be for every data we want to run the iteration, let's say few times, let's say 5 times. So what happens here is we are taking a data, we are taking the input and output, we are adjusting, we are taking another data, again adjusting. Like that, we are training the model. But for every data, let's say I want to adjust the weights 5 times, then move on to the next one. So we want to use another nested loop again. So for that purpose, let me create another loop. So we have k, so let's say L, and L should be less than our epochs, and then L plus plus, and this will end at here, somewhere here. Okay. And here we want to write another thing, and this is basically what are the things that we are getting in every epoch. So here we will write epoch of $L, and output is what? So output is basically our output value, right? So now and also let's do one thing. Let's comment out these lines because it will become more clear like that. So hidden errors, whatever. Let's comment out these lines. Comment, comment, hidden values. Yeah, I think that's all. Now again, let's run this thing. And as we can see, for every iteration, there are 5 epochs. Now let's see. So our input is 10 and -5, output is 5 and 15. And as we can see, it is very close. It's not exactly there, but it's very close. So here, the first one we have 4.6, 15.6, and then it is gradually getting adjusted. Okay, so there they did a mistake once again. So 4.88 they reached close, but they again came back. So yeah, so sometimes neural networks will have little bit of issues like this. But yeah, it's getting close, right? So here the output should be minus 17 and minus 1, and here we have minus 17 and minus zero point 0.9. So it is almost there, almost there. Let me take 200 instead. Now again, let me run. So for iteration 199, input is 11 and minus 1. Okay, so output becomes nan. I think we are having some issues. If we try to find out. So up to 100, I think it was working good, and then something happened. So here, 6 minus 6 in 125. So the output is this one and this one. Oh, okay. Yeah, so we are getting some issues. So issues is divergence. So divergence means, so what happens is the neural networks when they're training the models, so when we're adjusting the weights, it will try to converge it into a one point. But sometimes what happens, the value of the weights and whatever we are using to adjust, it becomes so large that instead of converging to the result, it starts to diverge. And by diverging, sometimes the values become very big. And this is the limitation of our small network and our like everything small, small things. There are a lot of things that we may need to do to fix this. But yeah, we can make a small network like this. So for example, here if we see, yeah, so here the output is coming as infinity. And this is the problem, I think, why we are getting this kind of issues. So let me, so after the infinity, everything is like bonkers. If we take smaller numbers, like from minus 7 to plus 7, it will work much better. So for example, 0 and minus 4, okay, it is minus 1.88 and minus 0.258 or whatever. This is 11.3 if we, okay, let me take 100 only. We are doing too much training, I think so. Yeah, if we take 50, I think it will be even better. Let's see. So 3 and 7. So 3.4 and 6.0, 2.3 and 2.9. It should be 0.6 although. Minus 5.31 and minus, it should be minus 6, minus 6. So yeah, it's going there, but it's not exactly there. But yeah, but the point of the video, I believe, is clear that how we are basically adjusting the weights, and this is something, yeah, that we will discuss more in the future. But yeah, lastly, with one thing, after doing one thing, we'll close the video, and that is we have lots of weights and biases. So, what do we mean by training a model? It means basically adjusting the weights and biases, and then those weights and biases can be exported so that other people can use that model without going through the training. And to do that, we can actually export our weights and biases here in a JSON format. So, we will do a weights data, and here we will keep all our hidden weights, then the hidden bias, then the output weights, and the output bias in a weights data. And then we can write this in a JSON file. And to do that, we need another module, and this is the fs module or file system module. So import fs from fs, and we can write fs dot write file sync, and let me name it as weights.json. And here we will do json.stringify, and here we will keep our weights data, and then null 2. Formatting will be utf-8, and here if we once again run, uh, this is not the best model to export. This is not something that you can, you definitely, this is not something that you want to show it to others. But yeah, this is only for learning, but this is how we can get the weights. Yeah, I mean, this model doesn't do anything. This is such simple arithmetic that we can do by counting in our hands, and we have trained a neural network and it doesn't even do a good calculation. Yeah, but yeah, you can get weights like this when you train better models, and yeah, we will definitely do so in the upcoming videos. So yeah, that's it for this, folks. And if you've learned something new in this video, make sure to like, share, and subscribe. And I will make a lot more videos on these topics going forward. Yeah, so see ya.